discussing on to the yet another aspect of real-time system design, that is understanding the real-time operating system. Okay, so today's objective is to find out the basic concept that we call as a real-time operating system, which you have discussed in the past in brief, as well the services those this operating system would cater in order to govern the service time, which would be extremely useful for design and development of real-time system. This is what the agenda that we have for the today's discussion. Okay, so the outcome after discussing of this particular session is we should be able to understand the differences between RTOS, that is real-time operating system, and GPOS, general purpose operating system. Okay, so let's start discussing with the basic content, like what RTOS is all about, why it is being used, what are the differences between RTOS and GPOS, what are the different components of this real-time operating system, how does this real-time operating system would offer the services in different fashion. So what are the different mechanism that is being undergone in order to give the required deterministic service time by different services of operating system, that is real-time operating system, and what kind of additional services that this real-time system would be providing in addition to what we'll be discussing throughout this particular session. Okay, so maybe this particular diagram is definitely not new to anyone. This is talked for at least 4 to 5 times in the past. So whereas I understand that the RTOS or any operating system being an interface between the application software and hardware, this interface necessarily getting served at both the ends. The application end of interface is called as an application programming interfaces. As well, the hardware end of interface of this operating system is referred to be as an port that we have seen in the last couple of sessions. Okay, and RTOS is definitely not different than the operating system concept that we have seen. Only way in which the services of this particular operating systems are offered, that is somewhat different. Okay, if you remember, then while discussing the software architectures of embedded system, we have discussed about, am I audible?
Yes, sir.
Do you get any lag of my voice at your end?
No, no.
No, sir.
Okay, then it might be my local issues. Okay, fine. If for you it's fair, then I can continue with it. Okay, fine. So as we have seen that RTOS happens to be one of the software architecture that we have seen in the embedded system, right? And we have seen that when we are supposed to design a real-time system, which is a subset of embedded applications, then we understand along with the functionality, the timing of that particular output plays an extremely important role. And that is what these particular real-time operating systems are more concerned for timing control, that is establishing the control over the timing. And establishing control over the timing cannot be done at gross level. It has to be done at the different task level. That is what granularity comes into the picture. The number of tasks that I would have better control. I would have better ability to control this individual task, and I can have the control established over the gross for the application. This is also what we understood in the couple of last sessions. Okay, the point to discuss at this moment, when I'm saying RTOS is a software architecture, that is referred to be as ideal worst case zero latency time, means the instance at which the service is being expected, at that particular instant the service would start governing of it. That means there will not be any response time for either an interrupt or for a task to get executed from this RTOS. Though we are saying it's a zero latency, this zero figure is being there in an ideal terminology. In practice, every service or every interrupt has got its own latency, and this particular latency becomes a feature of a real-time operating system. Okay, so and the manual of real-time operating system clearly mentions that what is the worst case latency that you can expect from this particular OS in order to design your system based on it. So that particular aspect is also expected to be known in advance for it. Okay, fine. So when I'm saying it's an software architecture, I know that this particular software architecture is nothing but it's an operating system itself, which is being used for giving the service time in order to design and develop an applications, that to real-time applications. Okay. So what this RTOS is all about, this RTOS is nothing but this is an operating system. Why this RTOS is being required? Whenever you want to establish some certain control in the execution time of an application, and if that particular control cannot be there only with a general purpose operating system that you would use for it, or that control cannot be established with the different software architectures as such, like round robin with interrupt or function queue scheduling, or your own methodology in a concurrent or sequential fashion of execution. So either of doing all the things, if you really cannot meet with this particular deadline, with this particular estimations which are being given for execution of an application, so during that particular time, RTOS would come to rescue. This is what the reason why this particular RTOS would be used. And one more reason, which is very solid in order to discuss into this particular session, is the service time of this operating system would always be constant, deterministic, and more importantly, it would be available, it would be aware, it would be letting us know well in advance before using it. This is the most fundamental and crucial significant aspect of real-time operating system in the design of real-time systems. Because something which is an operating system service time, though we refer that to be as, I repeat, though we refer that to be as an overhead, because that doesn't really directly contribute to the functionality of your application, still that overhead also should be known well in advance in order to take it into account for the complete state of execution time of this particular operating system, of this particular application. And that is what we really intend to understand it in a nutshell, like what this how this particular service times or operating systems are being governed for it. Okay. Now, as we know that there happens to be different approaches even for the real-time operating system. Monolithic, where all the sets of services are being bundled together. There is no granularity, there is no modularity as such into the service offering of this particular OS. We do call that as a monolithic. Second one is whatever is being required, only that portion of the service is being expected, and whatever bare minimum required, that will be the service that would be given by an operating system, and whatever you will require during an application, that could keep on adding onto that particular operating onto that particular application. That is, the memory optimization is the basic role that would get played with this particular microkernel approach of this operating system. And third one, as we discussed, the decoupled, where the real-time and non-real-time components are different and they have to be patched with each other in order to have the real-time and non-real-time task. We need to identify real-time and non-real-time task, and then we need to decouple this real-time, non-real-time task with a separate set of OS in order to give justice or priority to the classified real-time tasks that could offer a priority and that would go on execution with an expected line of operation. So this is also a benefit that would get with an decoupled approach of this particular real-time operating system. Okay, so let's go quickly with understanding of what are the basic difference between the real-time operating system and general purpose operating system. Okay, so as difference formally that we say that this key difference in the RTOS and GPOS, that happens to be deterministic service time. Okay, this is a key difference. Along with the other difference, now why this particular deterministic service time would get offered? Because RTOS will provide the service time which will not be a function of underlying load for which the service is getting catered. What does it mean? It means that whatever the number of tasks that I might need go for management, whatever the number of messages, irrespective of length of the messages that I would go for inter-process, inter-task communication or synchronization, whatever the chunks of memory that I'll be using it for the management side of it. I mean, irrespective of the number of or volume of the service or number of tasks those are involved into the service time of the operating system always happens to be a constant. And that is what we say, that it is a load independent timing. What does it mean by load independent timing? Load independent timing refers to an ability of an operating system to provide the service which will not be dependent on the volume of the tasks to be performed by an operating system, as well as the number of tasks those would be performed with that kind of volumes. Okay, and we'll see an example in the case of task management service of operating system very clearly. Okay, at the moment the prima facie difference that happens to be deterministic service time, and this deterministic service time, by virtue of mechanism that it offers, is constant and load independent timing from RTOS as compared to GPOS. Okay, the task scheduling that happens to be there in a different way. Okay, most of the real-time operating system, as we understood, is believed to get scheduled the task with the help of priority-based preemptive scheduling kind of algorithms. While that is never been the case true for general purpose operating system. This is also one of the major difference. Then the fixed time task switching, that happens to be a major difference whenever we are saying it's an task management service of an operating system. So how does that happen? That we'll see into the next couple of slides. So I just remember that the fixed time task switching is basically irrespective of the number of tasks that it keeps on coming. The task switch time always happens to be same, always happens to be constant, and that is being known a priori. And that is what I can estimate number of I can estimate the total execution of the application irrespective of the number of task switches that would keep on into my systems. So again, this particular point is very much related with this load independent timing or load independent service offer time of this RTOS. Then intertask communication and synchronization happens to be also in the same way, where irrespective of the message length or irrespective of the number of messages, this particular RTOS service, intertask communication and synchronization, would offer in the different way. Okay, and then deterministic and high speed message passing. That is also one of the very interesting aspect of real-time operating system that might not be the case with the this general purpose operating system. Okay, and the dynamic memory allocation also happens to be in a different way, as we already seen it, like for embedded system, what kind of dynamic memory allocation that we'll expect for it. Okay, that we discussed in the last with reference to an RTOS, we'll discuss in this particular session. So in gross or in a nutshell, I can say that this particular real-time operating system does not offer the different services, but it offers the services differently. So mechanism of service offering is different than GPOS. And what for the different mechanism is being adapted or is being designed? This is adapted or this is being designed in order to guarantee a constant, deterministic, and known a priori service time. I think this is what the features of service time, characteristics of service time of RTOS, that by this particular time, each one of us has really understood and each one of us has really remembered it to a larger extent, isn't it? Because this is really the key parameters, key aspect of real-time operating system. Okay, fine. So if you refer this real-time operating system component of this operating system, you would get to know that the scheduler that would take an input from real-time clock, the scheduler information that might be in the form of your task control block or process control block and all that, maybe interrupt handler, what kind of interrupt priorities and all that is being there. So this is also happens to be one of the interrupt. Then this particular scheduler would dispatch the task based on its priority, based on its preemption policy, to a process awaiting for the resources. It would be planning for that, right? Then the resource manager would take this input as in a process ready queue or waiting queue, as well as the process resources requirement that would be gathered from the applications, as well as available resource list, which is referred to be as an waiting list or the ready list that would be available for the resource. Okay. For that, the input of this particular available list is being given from the dispatcher. Okay, and then for this particular dispatcher, if my system happens to be with a different core of the processor, then processor listing that even can be having to end this particular dispatcher. Means in nutshell, if you see this scheduling, process resource or resource manager, and the dispatcher, these happens to be the three basic component. This happens to be the three basic component based on which the real-time operating system would cater its services. And these are the different environments or these are the different factors which are being there inputted or which are being there used in tandem with each other in order to govern the service for either scheduling, for resource manager, or maybe with an dispatcher of it. Okay, so this is what the classical component listing that is being given for this real-time operating system. Okay, fine. So moving ahead, this real-time operating system, the kernel that we called even to be as an RTK, that is also called real-time kernel. RTOS can alternatively be referred as an real-time kernel, RTK. Okay, so this particular RTK or real-time kernel has got the basic services into it, and these basic services are basically like intertask communication synchronization, timer, device IO supervisor, dynamic memory manager. Okay, and in center as a core of this particular service, which happens to be as an scheduler, or we do call that as a task management. It's not only scheduler, it's going to be a task management. For the gross term that we'll use for that particular service is task management. It might incur the task switching, it might incur the scheduling of that particular task. So in general, the task manager is basically there as a core service of this RTOS, and around which I can have the different set of services, which is bare minimum and mandatory. So this set of services happens to be this ITDM, intertask communication and synchronization, timer, device IO supervisor, and dynamic memory allocation. I do remember these particular services, the essential services of RTOS, with a term called ITDM, the initial letters of every service that is being remembered with me for so many years of it. So whenever I say it's a RTK service, I just say ITDM. So it's this kind of services are being there, which are centered around this task management. Okay. Now we'll see what this particular services of task management, how does this particular RTOS would provide this task management service differently. Okay. Like most of the category of this kernel services that happens to be as a task management service, undoubtedly that we all agree with it. Okay. Then what this particular service would facilitate? This ability to schedule the task, ability to entertain n number of tasks in order to get proper scheduling time, proper CPU time, encourages or facilitates the application to be modular in nature. And that is what we in general say, that this task management service even might inculcate or facilitate the modular design of an application. Okay, this is a tangible benefit that you would get with the help of this task management. Each separate chunk of a software is called a task, a simple definition that is being referred to be as a task. Okay, so when I'm saying it's a separate chunk, that means that this is sustainable executable entity. And that's what we call a process or a task interchangeably, as process also gets defined to be as a self-sustainable programmable event. A self-sustainable programming event is referred to be as a process. Likewise, the task can also be given to be as each separate chunk of software that is we refer to be as a task in the literature of this real-time operating system. So ability to launch the task and assign the priority is basically the functionality or is a subpart of this particular functionality of task management. Then scheduling of the task by virtue of scheduler. This is a bare minimum or mandatory service that we all know. Then task scheduler controls the execution of application software and can make them run in a very timely and responsive fashion. This is what, in order to prove this particular statement, we need to understand how this the task management service of RTOS is offered. How does it offers in a different way? Okay. In order to get it understood very quickly, let's try and understand this diagram. Okay. So this particular diagram is taken from one of the white paper, which is being mentioned as a reference at the end of this particular slides, or even you can see that this particular reference with this, the discussion that we are trying to make at this particular moment is after this particular point is more or less based on the very famous white paper that is available, which gives us the basics of real-time operating system. Okay. And this particular website facilitate us for that particular literature available to that. Fine. So what do you get to know from this particular diagram? You can understand that for general computing or non-real-time operating system, if task switching time, if we maintain that on the y-axis, and the number of tasks that are required to be scheduled, if we maintain that on the x-axis, then you definitely get to know that the for this general purpose or for the GPOS, we'll see that the task switching time is a function of, maybe this is task switching time is a function of number of tasks that can get scheduled. And you'd get to know more the number of tasks. You might see that it might go with a linear proportion, it might go with this particular non-linear proportion. Okay, so this particular proportion that indicates that the task switching time becomes the function of number of tasks. And there we have an issue for non-offering, or we have an issue where this GPOS cannot offer me the constant and a priori known service time that I would call to the task switching time. Because task switching time, unless it is not being constant, as I said you, I cannot take it into account for estimation of the complete execution time of my application, because my application having n number of tasks. So if my application has got n number of tasks, I do expect n minus 1 task switches that would happen with that application. So I would come across n minus 1 task switching time, which would be added as an overhead along with the execution of that particular task. And if I know that in this particular deterministic and algebraic fashion, then shouldn't it be known that this task switching time should be always constant in order to give me the highly predicted complete or the total execution time of the application? Yes, we need that kind of feature. And this kind of feature is provided by this real-time operating system. If you refer this graph, which is being given with this particular line, green line, you will see that the task switching time is independent of number of tasks. That is what we mentioned in the last slide, the statement that the service time happens to be independent of load. And in this case, number of tasks that is to be scheduled becomes a load for that particular scheduler. Getting my point? So I think this is very straightforward and very clear. Okay. Now the question that arises is why this particular, what is the mechanism by virtue of which this RTOS would be able to offer me this particular task switching time, which is independent to the number of tasks that can be scheduled. Now let's try and understand first of all, what is the mechanism that happens into the GPOS and why this particular GPOS offers task switching time, which is dependent on the load. Let's understand that first. Now, when we see task switching time, this task switching time is a function of n number of activities that keeps on happening. Isn't it? The number one activity, or on a priority basis, I would say, the amount of context that it needs to store and restore back. This is one of the prima facie, or this is one of the very significant activity that happens, right? The second part is what is the location or what is the resources in which the context is being saved and being retrieved, or being stored and being retrieved. If it is there into the memory, then we understand that the memory latency times would never be an uniform, would never be an constant. That keeps on adding its variability, that keeps on adding its undeterminism or non-determinism, because of the memory access times are never being an uniform and constant. That is also one of the reasons. Getting my point? So these two are the prima facie important reasons why the task switching time in GPOS will not be always constant. And it is always going to be dependent on the number of tasks that would get produced. And the better example, needless to say, that when we have something like 8-9 browsers, those are being opened, some MATLAB or some kind of multisim or some kind of rendering software is being there running on your personal computer, then you definitely know that the speed of the computer that becomes very slow. And at some certain point of time, you would say that the system is hanged, because it would not respond to any activity of the user. It would not respond to any of the functionality of the user. And that's what we declare that system is hang. Let me tell you that there is no word hang into the computer literature. Okay. We are not having that much patience to wait for the task switching time, which has gone very high because of more number of activities, more number of tasks which are being involved into it. Getting my point? And that is what the reason why we declare that system to be hang. You can make a simple experiment, like when you get caught into such kind of situation in the future, you can just keep that system rest for some amount of time, and you come back and you'll get to know that system started functioning. If that would have been hang, then what are the reasons by which it would get function? Getting my point? So release of the RAM, release of the memory manages chunks, those are being occupied by the different earlier task. That becomes the reasons why this particular GPOS will not give me the constant service time. As against of that, when I'm using the scheduler from real-time operating system, okay, it is never that the scheduler of operating system, okay, it's never that the scheduler of the operating system is being loaded by the number of tasks, and it is with the reason that it is not the scheduler that has to transverse for the tasks. If I have got 10 tasks, and if my scheduler start making the status of each and every task at some moment, okay, and if it is being decided that, okay, fine, 1 to 10 tasks are there, so scheduler is first of all going to refer the task control block for task number 1, 2, then 2, 3 in that sequence. Then when if that scheduler is transversing the task control block or the control data structure of scheduler in order to decide which tasks are to be scheduled after the current one, then the service time would never be constant, because it keeps on proportionately incrementing depending on the number of tasks that would keep on incrementing. It's as simple as this. So as against of this, what RTOS mechanism would do? This RTOS mechanism, in a simplistic way, rather than making a scheduler transfers to all the task control block, what it would do, the task control blocks are being arranged, are being there in such an encoding fashion that whatever the task that becomes ready, that particular task will raise the flag. That particular task would get into the ready list, and among the ready list, the scheduler of operating system would get to know by priority encoding mechanism which is the highest priority task that has to be scheduled. It's not like it has to transverse through all the task control blocks. Getting my point? So it is as simple as that. Okay, it is as simple as that. Like if, for example, you are now around 16. Okay, in a 16 students, if I keep on asking individually, turn by turn, whether you understood, in that way, I would be transversing through all of your existence in order to check that are you getting what we are discussing at the moment. As against of that, if the declaration happens that those whosoever is not able to understand, he should raise the flag. What does it indicate? It simply indicates that this scheduler does not need to consume a time in order to transverse through all the task control blocks. This is the prima facie mechanism differences by virtue of which this particular real-time operating system would offer constant, deterministic, and known a priori service time. Now, let me ask you one thing, that from this particular diagram or from this particular graph, does it get claim at any point of time that the service time of real-time operating system as a task switching time is less than that of GPOS? Because there are many instances at this particular moment you can understand that the GPOS service times are far better than real-time this RTOS service time. GPOS service time is less than that even of RTOS service time. So is there any point in referring that RTOS or real-time systems would always be a faster one as compared to general purpose systems? No. That were never being a notion even theoretically as well as practically. That's what I said, like the real-time operating system does not offer the service, okay, does not offer the service in a faster way, or the service time doesn't happens to be a fast. But what is the characteristics? I repeat it one more time. It should be constant, load independent, that is deterministic, and should be known in advance, because this time is going to remain constant. For a given specific RTOS, this particular time is going to be constant one. That is the typical way by which the RTOS would offer the service called as a task management service. Okay. So I hope you understand this particular task management service. How does it offers and how does it offer in different way than the GPOS? Okay. So let's move on to the next service, which is what? Intertask communication and synchronization. So let's discuss it very quickly because you understand this intertask and communication service very well. Okay. Now, when you say there is a producer task or transmitter task which sends the messages, these messages are supposed to be received by consumer task or receiver message, right? This we have seen into the unit number 2 itself. Okay. The mechanism that is being used for this intertask communication and synchronization, we have seen that particular mechanism to be either the shared data or an IPC. Okay. Let's discuss at this moment an IPC. Okay, the inter-process communication, it may be a mailbox, it may be a message queue, it may be an event, it may be a pipes. So all these operating system primitives, which are referred under the category of this intertask communication and synchronization. So you can get to know if I want this particular service time of intertask communication and synchronization or intertask communication service time to be constant and should be independent of the load, what kind of mechanism it has to use. This is what we need to understand as how does RTOS would offer me the different, how does RTOS would offer me the services which would be different than general purpose operating system. Okay. And that is what like we get to know here, that this particular sender task or receiver task communicates with this particular, for example, mailbox. Okay, this is referred to as a mailbox. So if we communicate that with a mailbox, what it does, it simply copies the message into the mailbox. Okay. Or in general purpose operating system, what it happens that this particular message is getting copied to this particular mailbox. Or if it is a memory, it copies that message to the memory, and the consumer task or receiving task is being known with the arrival of that particular message, so that this consumer task will take that particular message onto it. So how many times this particular memory access is being made? It is made at 2 times. One time, which is a write access time for the producer task, and read access time by the consumer task, isn't it? And as I said you that the length of the message is going to define this read or write access task. If my messages, do you expect that the messages would all the time be as an uniform length messages? No, I cannot guarantee an application that messages that I need to communicate among the different tasks, those would be of a uniform length, uniform time. No, some message would be of say, X bytes, some message would be of Y bytes, isn't it? So I cannot ensure that. So if I want the service time, which is intertask communication, to be made independent of the message length and independent of the message length, what I'm supposed to do? The simple strategy that is being used is, instead of passing the messages, why don't we pass the address of that particular messages? If we pass the address of those messages, that we understand address of the messages can be referred to be as an pointers, isn't it? And pointer size variable is always fixed, right? If I define that to be as an 2 byte, then pointer size variable would always be 2 bytes. Now, in order to communicate that pointer size variable as against of the total message, I would each time would require the same amount of time. And as the length of this pointer size variable, which is 16-bit, which is constant, the time that it will require in order to communicate that address of the message in the form of pointer, that always be constant. Getting my point? So with the help of pointer, have I communicated the message? Yes. Messages are communicated. Getting my point? The consumer task would get to know what is the location of message so that it can go there and fetch the message. Instead of communicating the message itself, if I could communicate, instead of communicating the messages itself, if I could communicate the message pointers, then definitely I expect that the service time would be always constant and it should be known a priori for it. Okay. And this is what we say, that RTOS would offer even inter-process or inter-task communication time also to be constant and also to be known a priori, because the length of the or the pointer size variable is 16-bit. So it will take the same amount of time each time. So definitely it will not be having that kind of issues in order to communicate with even the length of message happens to be a variable one. So that is what we are cutting down the dependency of length of the message by passing the pointer. That is what we making the service time to be as an independent of the message length, independent of the load of the communication. Okay. And that is what, even in our experiments also, even in our lab setups also, in the MuCOS 2, when we are going to make use of the mailbox service, so we are going to pass the mailbox with the help of pointer. Okay, that is also the reason that I thought I should let you know well in advance for it. Okay, fine. So what is the key that we have discussed out of it? The key is to pass the pointer size variable as against of messages itself. So this is what we get to know very early out of this particular discussion. Fine. Then timers, as since many embedded systems have stringent timing requirements, as we know, most of the RTOS kernels provides some basic timer services such as task delays and timeouts and all that. Okay, so that particular services are being provided with it. The beauty of the service is this particular service times or service routines, most of the RTOS would provide you the service time or delays, like we have used in one of the things we have used into the OS time delay. This is a service routine that we have used for it, isn't it? So this particular service time, service routine that we used for this particular RTOS, okay? So this particular service routines happens to be an atomic in nature. And I don't need to tell you what the atomic in nature all means for it, right? So it is irrespective of the interrupt generation. It is uninterrupted services, those are being offered by the timer. Because as we are discussing real-time OS, as we are discussing the mechanism of RTOS to make the systems real-time, I cannot afford to lose any timing parameters of it. Because I might go with a control, I might go with, I might go with very investigative mind with finding out the status of the task in terms of its timeline also. So what is the amount of time that task has spent into this? What is the amount of time where the service of RTOS has spent into this particular task? So these particular status queries, when I'm making it from my application with the help of APIs, then during that, the timer becomes an integral part of it. Okay, even task control block also gets to know that what is the time at which this particular release time of that particular task is being there, how long that is being executed. Okay, so that you can get to know the CPU utilization factor, as we discussed last time, EI divided by PI, right? So execution time divided by total time of that particular task, right? So non-idle processing of the system is being given by CPU utilization that we have seen last time only. Okay, so these services are expected to be offered in an atomic way, not, and this GPOS will not offer that into an atomic way. Because that is not always being expected in GPOS, because GPOS means for throughput, not for establishing the control over the execution times. And RTOS basic requirement is itself not a throughput. This is basically in order to establish the control for my application. So that is the prima facie difference, and according to that, the services and the mechanism of services would keep on changing with this RTOS. It is always, as we say, by virtue of having an atomic timer routines in order to cater an accuracy. Along with an accuracy, it always gives me a high predicted service values of it. High predicted service times would always be given out of it. And that is what one of the value feature that, or value addition that is being there with an timer service of this operating system.